Welcome everyone to this Introduction to Scientific Visualization with Avizo workshop. My name is Thomas Teusel. I'm a visualization scientist at the Chaos Visualization Core Lab. So before we start, since you're here, you have received an email with this Zoom link, but there is also a link to our wiki page where you can download the datasets and slides for this workshop. And there is also more information on other trainings and in general what the VisLab does. So check this out. This workshop is being recorded, and I'm going to put it on our YouTube channel, where you also find all the other recorded workshops. So before I start the workshop, I wanted to talk a little bit about the Visualization Core Lab and what we do, what kind of facilities we have, and what services we provide. So the Visualization Core Lab is one of 11 core labs, which are a support facility for research here at KAUST. You see all these different labs. If you find something that sounds interesting for your field, for your research, make sure to check out the other labs as well. The Visualization Core Lab is together with the Supercomputing Core Lab. It's the research computing facility, and you see the facilities director, Jisoo Lee, there on the left. This is the KVL, Chaos Visualization Lab team. You should meet the other guys, Soheb, Dina, and David in other workshops. I'm here today, and Gendon is in the background. He's going to help with answering questions. Thanks, Gendon, for doing this. So here's what we do. So essentially, our core services come in three groups. We provide facility support. So we have special visualization hardware like virtual reality, head-mounted display environments, style display environments, a multi-purpose auditorium, and other high-performance visualization hardware. So that's what we support. But we also work on projects with data visualization and data science workflows. And we provide trainings and workshops, and this one is one of them. And in order to do that, in our group, we have expertise in HPC visualization, 3D reconstruction and visualization, in a large-scale data science, and at large-scale visual analytics. And you see here some of our facilities. This tile display wall, this large one, you might know it if you go from the library towards the IT building. It's on the right side. And here you see a scientist looking at the neurons of a rat's brain. That's a very complex data set. So the more space you have, the better. On the top right, you see a similar data set, also the neurons, but this time inside a six-sided cave, which we call cornea. So you have fully immersive virtual reality environment. And then we have two smaller scale semi-immersive virtual environments, which we call the cubes and Zone 5. And we also have a multi-purpose room with state-of-the-art audio and video hardware for presentations or showing 3D videos. What I want to say here is that you can book these facilities yourself. You need your portal credentials for that. And if you've never used them before, you might need to get the keycard access and probably an account on our systems, but that should be done in a few days. The most important thing here on this slide is actually the last line. Whatever if you require help, just shoot us an email at help@vis.chaos.edu.sa. I will show this email address a few times again, and you have actually, of course, as I said, access to these slides in your download. So here are the workshops that we do this spring semester. You're in the third part of the Scientific Visualization Workshop series. The first two have already happened, and the first one is actually already on YouTube. The second one should be there soon. The first one is an introduction to scientific visualization with ParaView. There's a small overlap with this one. The first session on scalar field visualization is similar, but then the rest of this workshop is actually targeted specifically to Avizo. If your workflow involves things that we do in the second session on volume segmentation, I want to point out the fourth part of this series, Introduction to Image Segmentation and 3D Reconstruction. That should be very interesting for you. It will be this Thursday. There's still time to register for that one. And then we also have a data science workshop series. which is mostly done, but the last two are this and next week on machine learning and deep learning. And the first ones are already on YouTube. You can check them out, and I would actually encourage you to do that. They are probably useful for all kinds of scientific workflows, not only data science, although data science probably is everything anyway. But if you have to deal with a shell, conda, Python, Git, or SQL, SQL, sometimes it's called, then you can check out those workshops as well. Okay, so what we're going to do today? Goals and agenda. First, the main goal of this workshop is to do an introductory course for hands-on learning with Avizo. I'll do it in essentially from two different sides. On the one hand, I'll do hands-on sessions to show you how to work with Avizo, but also hands-on sessions to learn the basic visualization techniques. And the way I've chosen to do that is I've recorded tutorial videos. I will play those videos. I'll do it somehow conference style. And after each video, which is about 10 to 20 minutes each video, I will have a Q&A session. So feel free to ask any questions in the chat anytime. And during the Q&A sessions, if you want to clarify something, just unmute yourself and we can talk about whatever you want to know. So what is Avizo? Avizo essentially is a commercially supported software platform for 3D and 4D data visualization, processing, and analysis. 4D in this case means it's also can handle time-dependent, time-varying data, but we're not going to do this today. So Avizo started actually as a research project at the Zuse Institute in Berlin, and they called it Amira. That was a rather successful project in the 90s. So the Visualization Sciences group in France actually continued to work, but they actually started a complementary product and called it Avizo. And then finally, in 2012, FEI purchased VSG, and now Amira and Avizo are back in one hand. And eventually in 2016, Thermo Fisher bought FEI. And that was what it is now. And the reason I'm telling this here is that sometimes you see things like Amira/Avizo. They are essentially the same things. There are minor differences, but you can think about, especially when you start doing your research and your visualization and analysis workflows, then you can just use Avizo, and that's what we're going to do today. And the second thing is that Thermo Fisher now owns Avizo, and that's the reason that some of the slides contain their logo. So here is one which shows what Avizo actually specializes in. So it's in principle a general purpose visualization tool for all kinds of 3D or 4D data, but they specialize because of the nature of the company, Thermo Fisher, on certain things like the life sciences, natural sciences, and material sciences, and also industrial inspection. So if you want to look into your machines that you build without destroying them, then you can do a CT scan of them and use Avizo to do that. Use Avizo to visualize and analyze with the goal of understanding your data. And the way that Avizo can help you with that is like here's a typical workflow. So from the data acquisition, when you get your data from whatever scanner, maybe using the imaging core lab, until to the presentation, at the end, usually you want to somehow present your work. That can be in a paper or your thesis defense or a project proposal, whatever. In between, Avizo can help you with all the steps that you need to do from data import to filtering and preprocessing, visualization, segmentation, and measurement and analysis. And we're going to touch on all of these steps a little bit. We'll be focusing on visualization and segmentation. So how can you use Avizo here at KAUST? So first, it's a commercial product, so it's actually installed, or the installation and licenses especially are maintained by KAUST IT. You see the link to the Avizo software page on top. You can download binaries for Mac and Windows there. If you use IT maintained Linux workstation, then all you have to do is say module load Avizo, and you can use it right away. In any case, if you have any problems with the installation or the licensing, go to the homepage of IT, scroll down a little, you'll find these ways to get in touch with IT, and they can help you with these issues. If you want to use our expertise expertise at the visualization core lab for actually using Avizo and doing your scientific workflows. Again, I show this email address here. Feel free to contact us anytime at help@viz, and we will try to help you. So what we're going to do today is, after this introduction, we'll have essentially 3 sessions. The first one is on scalar field visualization. Then we'll do a short break. And then we'll have a session on volume segmentation. And again, after a short break, the last session is an overview of the Avizo GUI and features. That's not going to be a comprehensive overview. Instead, I've chosen to select a few issues and record a few videos on doing some things, generic usage of Avizo, things that I would have been happy if someone had told me when I started. I hope they are helpful for you as well. And in the end, so if you add up those numbers, there should be much less or somewhat less than 4 hours, the time that we have. So we should have enough time, especially at the end, for Q&A and discussions. And here's a quick overview of the first 2 sessions as a short appetizer. So in the first session, we are doing some scalar fields visualization. We're going to take a look at the CT scan of a human head and explore it using basic visualization techniques like slicing, isosurfacing, and raycasting. And you see examples of all of these 3 techniques in the first row of the images. And the second session is we're going to look at volume segmentation. We're going to use another CT scan, but this time of a rock sample. And we're going to look at techniques like thresholding and the Watershed algorithm to segment the rocks. And we also have a short introduction on how to use the segmentation editor of Avizo. So this brings me to the first session of scalar field visualization. There is, let me stop the share and let me look at the chat quickly. Oh yeah, so you got the link to the training page there. That's good. I will just start the first video on volume visualization. All right, so before we do some actual scalar field visualization, we want to load the data. So when you start Avizo, you are presented with a welcome screen like this, where you have, for example, some news here, and you get some useful helps to links to help to documents. And you're essentially presented with 3 different options. You could create a new blank project, or you could open a project, previously saved project. We don't have one yet, so we want to actually open some data, which will also create a new project. So we just press open data here. And I want to quickly talk about 2 ways to load data that Avizo does not automatically support. So if your data is in a format that Avizo supports, usually called AM, you just select it and load it. But there are cases where this is not the case, and one, for example, is that you're given an image stack, like this one here. This is just a bunch of PNG images. You can scroll through all of them. Like, for example, for an electron microscope or a CT scanner, and they are meant to be stacked on top of each other to make up a volume. To load those images as a volume in Avizo, we just select all of them, press Ctrl-A. That's why I put them into its own directory, so I'm only selecting images that I want to select. Actually, if there are other files in this directory, I could just select the first one, go to the last one, press Shift, and select just all of them. Or I could just select a subset of the images if I don't want to look at all of them. But in this case, I want all. So to make sure I have all of them, I press Ctrl-A and say Open. Now Avizo presents a dialog where first you see that we have selected 466 files. These are meant to be the slices, 466 slices of the volume. Each slice is an image which has a resolution of 742 by 742. Then we could choose which channel we actually want to use. You could, for example, have an RGB image, but you could now choose the red channel, green channel, or blue channel. We have only one channel in here anyway. We could choose a name for the object, which by default is the file name of the first file. I just leave this. And then we have to define actually the extent of the volume that we're loading, and we can do this in 2 different ways. If we know, for example, the physical size of the volume, we could just specify its bounding box. If you know, for example, that your sample is 1 centimeter by 1 centimeter by 1 centimeter from a CT scanner, for example, you could just put them here. From an electron microscope, you often have the specifications that, for example, the distance in X and Y between pixels is different. Let's say, for example, 1.1, 1.1, then the distance in the Z direction between slices. Let's say here 0.2. 0.1, 0.1, and 0.2. Now we could actually load them as multiple files. That's not what we want. We want to read them as one volume. So we just press OK. Avizo loads, and we are getting this. Move that. We get the our loaded data here. If you do that, you might already have a module attached here. The reason is that if you go to the preferences, edit preferences, they're usually in general. You go to the last thing, which is called auto display. You can, by default, I think this is turned on, so you can automatically attach modules to certain kinds of data, and these are images, so you might already see an author slice. For label images, also get an author slice, surface nothing, and everything else would be a bounding box. I don't really like that feature, so I usually turn it off. That's the reason why I don't see anything. I just want to look at the data at the moment. So here, when you select it, you get a little overview of what the data looks like. So again, we have the resolution 742 by 742 by 466. It's a grayscale, 8-bit unsigned. That's what is specified. So the values are between 0 and 255. The memory is not that much, just 250 megabytes, a bit less. And the physical size now is actually, since we said it's 0.1 in X and Y direction, it's a 1/10 of the resolution, and in the Z direction, it's a 1/5 of the resolution. You can see the voxel size here, 0.1 by 0.1 by 0.2. We have a little preview. This is rather helpful often. So we know we have read the data correctly. But for the first part, I actually want to use a different data set. And in order to load that one, let's first undo everything. We can always do that by just saying new project, which essentially just discards everything and starts a fresh project. You could save everything before you discard it, but we're not going to need it, so I'm just going to discard everything and remove anyway. So the second case that sometimes your data is given is what is called a raw file. That could, for example, be when you're doing your own simulations in MATLAB, let's say, and you're simulating something and you're saving the results in a 3D array. And then you just say fwrite array to file. That's what essentially is a raw file. It's just a memory dump of an array. And we can load that in Avizo. So I have an example here, scal.raw. Let's open it. We can get a dialog where we can specify a lot of options, and actually this is very important. Everything has to be correct, otherwise the data will not be loaded correctly. So first of all, you have to know your data type. This is essentially the data type of the array that you simulated. You have the options between 8-bit, 16-bit, and 32-bit signed and unsigned, or 32-bit float, or 64-bit floats. Whatever you did, whatever that array was, I know in this case it was an 8-bit unsigned. And then you have to specify the dimensions of the array. That's also what you should know since you're doing it yourself. I know in this case it was 256 by 256 by 256. It's already there because I did that before. Avizo remembers those values, so that's sometimes rather useful. A good way to look if you did this, if you specified this correctly, is to see that the header is actually 0. So you're not you're reading all the data and nothing is left out, or you're not specifying too much. If you, for example, thought it was a 16-bit signed data type, then you see that your header would be negative, which is not possible. So this is not correct. We go back to 8 bits unsigned. And then we have to choose between big endian and little endian. In this case, it's big endian, and the X or the X facet is also okay. Again, we can specify the bounding box, either the bounding box or the voxel size. So the bounding box here would, for example, be between 0 to 55 in each direction, or the voxel size is just 111. I leave these values as they are. We load them, and they're here. So again, you have this little preview, which looks correct. We're seeing a little bit of the teeth of the skull. We're going to look at that later. For now, let's again quickly check if everything is correct. 256 cubed volume, grayscale unbit unsigned. That's fine. The memory size is rather small in this case, so 16 megabytes. And the physical size is the same as the resolution, since I left everything at 1. Here you see the voxel says again 1, 1, 1. So that looks okay. Now, if you wanted to load that at another time, you would have to specify all these values again. That can be tedious, so it's probably best to save this now in a format that Avizo can actually read. And you have two options here. You either save data as or export data as. And the difference is that in export data, you just have a lot more possibilities to store in all kinds of different formats. This can be rather useful if you want to use the data in a different program. In our case, I cancel this. In our case, we want to use it in Avizo again, so we save it as in a format that Avizo can read. And you have here only 6 options, and Avizo 6 are actually deprecated, so we have 3 essentially: binary, ASCII, or compressed. I think binary in our case is okay and the best one. We save this, and now we are ready to do some scalar field visualization. Okay, so this was the first part. So the first step in your typical workflow, that you have to somehow import your data. I hope that let me look in the chat. So Glendon explained a little bit how you can zoom in. I'm sorry about this, that it's so small. But we're gonna need the whole space of Avizo anyway later. So yeah, you can use these options to zoom in the parts that you're interested in. And again, you will have access to these videos. You can always look at them at your own pace, pause and zoom in and see what I'm doing and how to do this. All right. So anyway, so now we have loaded the data, and we can actually start doing some scalar field visualization. And let's go. All right, so let's do some scalar field visualization. First, what are scalar fields? So a scalar is essentially a number that usually represents some kind of physical quantity, like a temperature or pressure or density, and it can be given throughout a certain space, which can be 1D, 2D, or 3D. An example in 1D usually is a certain location over time. Let's say the temperature on your balcony over a whole day or over the whole year. In 2D, you can think of it as a temperature on the surface, or you put an object on a table and you want to know the pressure on the surface of the table, or you have a meter above sea level in a certain region, like here in this map, which we are all familiar with, and the usual way to visualize it is using these kind of contour maps. You could also draw it like a surface in 3D, but it's sometimes done, but it's not really as informative, and that's actually easier, and we also know how to use it. You know that if you're on this side of the mountain, and you want to get to the other side, that you can either take the direct route and have a nice climb, or you take a walk around, have a leisurely walk, but it will be longer. And in 3D, examples are, again, temperature in a room, for example, or pressure in a combustion chamber, or density of a head in a CT scan. That's what we are going to use now. So let's go to Avizo. All right, so we have saved the data in a format that Avizo can load. So let's just do that. Open the AM file. As I said, I have turned off the option that the author slides will be automatically attached. So if you already have one, you don't have to do this now, but I'm going to attach an author slice now manually. The way to do that in Avizo is you left click on this little triangle here, and you get the selection of all the modules you can attach. Another way is to just right click anywhere, get the same selection. Third possibility is if you've used it before on this module, you see it actually here. That's usually the fastest way. Anyway, left click on the display, you have an isocontours an author slice. That's what we want. Just hit create, and now here you see the author slice. The first thing you notice is that Avizo puts what they call a frame around this slice. You see it here. I think this orange is a particularly ugly color, so you can either change it here make it green, for example, or not much better, just disable. Okay, let's take a look what we can do. So first, a little bit about the interaction here. If you select this magnifying glass here, you can zoom in and out a little bit. If you want to move it around, you select this pen and then you can move it at a place you like. Okay, so we're gonna use that a lot. So here in the slice, you can first choose the orientation. We have the XY orientation here. You can choose XZ or YZ, 3 different axis-aligned directions. Let's look at the XY direction first. The next thing is you can choose the slice number. So we have a 256 cubed volume. That means we have 256 slices in each direction. Here we're seeing the slice number 128, and by just dragging this arrow, little triangle around, you can actually just browse through your data, through these slices. You might want to try to visualize mentally what actually is in this data. We know it's supposed to be a skull, so this probably is the nose. If we go further to the left, we see the teeth appearing. And this is probably the skin. And we can just slice through all the, browse through all the slices. And the next thing is that we can choose a different direction, orientation, slice through everything. So here you see the teeth appearing from this direction. Just slice through all of them. Here more teeth. In the third direction, from the back, obviously. The teeth are appearing now in front over here. All right. The next thing is that the data is shown as a color map. So we have the data range is 0 to 255. They're mapped from black to white. If you don't like that color map, you can choose a different one here. For example, physics. But for this kind of data, I think the grayscale is actually a good one. And yeah, we leave it like that. So one thing you might have noticed is that when we slice through the data, let's go back to XY, actually the slice gets smaller and bigger when we slice. The reason is that we are actually in 3D. So you're going through the data from front to back, and you can actually see that if you rotate the data a little bit. So you select this hand, and then you can just rotate around. You see that your slice is actually lying in 3D space. If you now move it around, you see it's going up and down. What you don't see is exactly the region where your data is defined. One way to show that is to use a module attached to the skull, which is called a bounding box. It's in the favorites here, or in this nice grouping under annotates. Annotation, bounding box, I selected. Now we see this bounding box, and we see exactly where our data is defined. And we also see that it has the same orange as the frame. And then since I want to see it, I actually change it maybe to white. Okay. And so here you can now seeing the region of your data, slice through it again, top to bottom, maybe in different directions. Avizo will always align it with the view that you're viewing. So you can rotate it a little bit to see that it's going through the space. All right, but let's go back to XY. What we actually want to do is we want to create some contours. Let's zoom in a little bit. The way to do this is that we attach a module to the author slice which is called isocontour slice. It's on a display, isocontour slice. And there we already see our few contours. The contours we're seeing here is, so you have two options to create the contours. The first one is uniform. Here Avizo will create this number of contours in this range, 0 to 55. So we see here that this is obviously not a good range. We're not getting any contours in all of this space. They're all around here. So let's just try to increase that a little. Now we have contours all over the place, but they're all in the same color. And although they're representing different values, a way to see that is to actually here use a color map to show the different values. Let's take physics again. All right, so we see the blue is the low values, and greenish, yellowish getting higher values, up to red, but we don't see any red here. The reason for that is that actually here in the color map, you see a little histogram in the background, and we see that we don't have a lot of high values there, but we're creating values for the contours here, so they don't really show up. We can change that by limiting the range actually of the color map. And moving it to the left, and now we see maybe a little bit too far. Go a bit back. So we see we have high values here, a very high peak, obviously, and going down to low values, blue. Okay, so this is a way to create the contour maps like we've seen before for an actual map of a slice of your data set. The other option you have here for the spacing is explicit. Here you explicitly specify the values you want to see. And by default, Avizo will create two values already in here. I just want to put in one for now, let's say 56. The reason for 56 is that if you slice through the data, this is approximately the teeth here. I could add more values if I wanted to, but just separating the space, they don't have to be in order, so I can add a smaller one and maybe a larger one. And now I see three different ones, for example. But let's stick with 56. And let's try to, again, visualize how the 3D object would look like. If we slice through the data, like this, from bottom to top, the contours on the slice, as we sweep through the 3D space, will sweep out the surface, which will be a 3D object that should look like a skull. And it's a good, here you see the teeth. It's actually a good exercise trying to visually or mentally visualize how this would look like. It's not an easy task. We'll use Avizo later in a minute to do that explicitly. And do it in a different direction. Maybe rotate again a bit so you see it. And see where your contours and where your 3D object will be. Okay, so let's try to do a 3D isosurface actually. Before I do that, a few words about the project view here. So you have all these modules that already keep piling up. It's a good idea to actually keep this a little bit tidy so that it's not too confusing. I like to have my data sources on top and then add modules to the bottom. But that's, of course, just a matter of taste. So we want to add an isosurface to the skull. So we click the triangle again, and we go to display, and here we have an isosurface. We create it, and there we can now select the one threshold. We take the same one as before, 56. Leave everything as it is for now, and then just hit apply. And there we have a 3D object. It is upside down. Here it is. The slice is not in the direction I want to. I put it in YC. And Avizo, of course, rotates again. So I rotate back where the head is. And this is what the head looks like. The skull looks like now as a 3D object. And if you thought that's what it is, yeah, then you're really good at this. So you can again try to just moving the slice up and down. As you're moving the slice up, the contours of the slice, the isolines on the slice sweep out this 3D surface. And that's what it looks like. The color of the isosurface is a constant color here, better than the orange, but I still don't like it. Let's change it to, let's say, white. Maybe that's too bright, slightly darker. That's better. All right, so here's this color. One option you have here is the draw style. I just want to show one, which is called outlined. If you zoom into this one, you see that this now actually is just a triangle mesh. So the skull, the isosurface is a surface, and is represented by a triangle mesh. And you see the triangle mesh here. Right. Let's go back to shade. So the next thing you might want to do is you could think, I could save this skull now as an object, as a mesh. And for example, if I want to process this in a different program like MeshLab or Blender for high quality rendering, but if you click the triangle here, you don't have any buttons for saving or exporting your data. The reason is that you can only save and export data objects, and data objects are in green here, and so you only have the skull here. Yellow means this module is a display module. It's only displaying things. So in this case, the surface is not really explicitly constructed yet. It's just being displayed. The bounding box and the isocontour slice are yellow as well. They are displays. The ortho slice is orange, which is also a display module, but the orange is supposed to remind you that it is actually slicing through your data, not showing the whole data. So in order to get actually an object that we can save to disk, we go to isosurface and go to compute and say extract surface. If we hit create, we get another module, which is red now, and red is a compute module. It's the first compute module that we created. What compute modules do is when you apply here, so you could change some options. There's nothing to change for us here. If you hit apply, it will actually create a data object. This is now green data object. So if you hit the triangle, you actually have the options to export. And you can choose again a lot of different formats. For example, Stanford PLY is a nice format, and I'll call it extracted surface. Keep the default name, and I save it. Now I have it as the mesh itself as an object. All right. And another thing is, so on the modules you see these little orange boxes here. What they mean is that this module is visible. So, for example, if I click this orange box here of the bounding box here, the bounding box disappears. It's gray. If I click it again, it's orange, and the bounding box is back. That's here is maybe a bit small. You have a larger version here, which does the same. Click it. Extracted surface doesn't do anything. You need to select the one that you want to show or not. Bounding box off and on. Ortho slice off and on. And the isosurface off and on. But we don't see an extracted surface here now. Even if I turn it on, because extracted surface is not a display module. It's not displaying anything. We have to attach a display module to actually display now the surface itself. And we can do that by going, again, clicking this triangle, going to display, and select, for example, the surface view. If you do that, there's our surface back. You might notice a small difference now is that it looks different because you still see the triangles here. The reason is that we have in the surface view an option on the more options. By default, we have triangle normals, so one normal per triangle, but we actually want the normals per vertex. then it looks smoother. It looks more like before. So the difference between the surface view and the isosurface, they're both display modules, but the surface view actually takes a mesh and displays it. The isosurface takes a volume data set and displays an isosurface in that volume. It does not explicitly create the surface yet. So if you now, for example, turn off the surface view and turn on the isosurface, you see that they are the same, but different representations. What you can also do in the isosurface is you have here on the draw styles more options. And for example, you can make it transparent. Make it a bit more transparent. So you see actually the contours on the slice through the surface. And this way it might be easier to visualize how the surface is actually constructed when you sweep your slice and the contours through space. This will create the 3D surface. All right. So let's go back to the shaded view. Shaded view on the surface view. Here. Another thing now is if you now change the isosurface, let's say you want a different one. Let's take 80. Nothing changed. Let's go back to 56. 80. Nothing changed. Even if we hit apply, nothing changes. The reason is that we're actually displaying the surface view, and the surface view is displaying the extracted surface. And the extracted surface is still the extracted surface that we generated from the ISO value 56 in this module, and this did not get updated yet. So we have to hit apply here. If we do that, we see that the isosurface gets updated. If you don't want to do that all the time, you have this checkbox here. We can say auto refresh. Now, if you go to isosurface and let's change it back to 56 and hit apply, it automatically updates. This is convenient, but can be dangerous if the data is large and it takes a long time to compute actually this isosurface. Then you have to wait a long time when you change things here, especially if you drag it around. Now there's no problem. But if you hit apply, then you change the value. You can even in this isosurface module check this auto refresh. And now the isosurface is actually updated every time while you are dragging around this triangle. This works since the data is rather small. But if your data set is larger, this you probably have to wait a while until the surface is generated. Even for the small one, you see that this takes a little bit until the surface is actually calculated. So this is probably this is convenient sometimes, but can be dangerous. All right. So these are the first few simple volume visualization techniques: slicing and contouring, isosurfacing. So it's just look at these modules, look at the options they have, and play around with them and try to get a feel how to use them, how to look what's in your data, and explore your data set. All right. So this was the first video on actually some simple volume visualization techniques. I think we can just go on with the next one, which is actually volume rendering. Okay, so we have looked at a few volume visualization techniques like 2D visualization, slicing images, and isosurfaces, which is called here indirect volume rendering. The reason is that it's creating an additional object, a triangle mesh, to render. There is a third possibility, which is called direct volume rendering, and this works without creating any triangle mesh or additional objects. It's working directly on the data and just changing the representation of your data. So without going into much details, just to give you an idea of how the algorithm works is, so you think of your data lying around in space somewhere here, and you want to look at it. So you want to look at it on your screen. So you define your image plane, and then you define your viewpoint, and you say, I want to know what I see through each pixel on my screen. So you shoot array through each pixel, and then you march through this this volume and keep accumulating values while you're going through the volume. This can be done in numerous ways. For example, you can just average all the values, or you can look for the biggest one, the largest one, to get the high intensity structures. Or the most general approach is what is called a transfer function, to use a transfer function, which means that you map these values you encounter along your array to opacities and color, and then make an image out of them. How that works is best to just look at it in Avizo. So I still have my project from the last video. I'm gonna keep it, but I'm not gonna show it at the moment, so I just disable them. And we want to do some volume rendering. In Avizo, there are essentially two ways, two modules to do that. You select your skull and go to Display, scroll to the very end. You have a volume rendering module, which says direct volume rendering of 3D images, and a module which is called VolRend, a bit more cryptic, and it says direct volume rendering of 3D images with shading effects. So we'll start with this one. It's actually a bit easier to use. Let's create this. And you already see something, but it looks weird. But before we look into this, the nice thing about this model is that you have three different modes, and the default mode is the most complicated one. This is volume rendering. But you have these two other ones. Let's start with the third one, actually. It's MIP, stands for maximum intensity projection, and it just computes the maximum along each array and displays that maximum. So there are no parameters here. You can change anything, but you see something, and it most of the time actually is really something already pretty useful. And you can rotate around, look at all the different things. You see clearly the teeth, the skull. So this is a very nice mode to just take a quick look at your data. If it works, if you see something, fine. If not, then there's nothing you can do. You cannot change anything. And another mode here is DRR, which stands for digitally reconstructed radiograph, which essentially means it's just simulating an X-ray. And it looks like this. Let's turn off the bounding box for now. And yeah, and that's what it is. It's computing an X-ray. Like if you go to the dentist, they take an X-ray of your teeth. But this has the advantage that you can rotate it around and look from all directions. And you have one parameter that you can a little bit specify the intensity of the projection. So you can play around a little bit. You get an X-ray image, which a lot of people are used to. So this is also a nice way to quickly look at the data and see what's in there. But anyway, the third one is then actually a direct volume rendering, and the VRT, T stands for texture-based, which is actually just an implementation. Detail is not so important. All right, so this looks a bit weird. Let's turn the bounding box back on. What's going on? In order to understand what's going on, we actually have to edit the transfer function now. So we do this by going here in transfer functions, color, to edit options and say edit color map. This opens, which is what is called the transfer function editor. And you see your color map. By default here, this is this VolRend red. Actually, I don't like that, so let's change it back to the grayscale. And we have this our usual grayscale color map. So we're mapping small values 0 to black, high values 255 to white, and in between we linearly interpolate. But in addition, you have this linear ramp here, which is the opacity function. Opacity is the inverse of transparency. It just means how much do you see that object, how opaque is it. And what happens here is that these low values here, they actually correspond to the air around the skull, somewhere here. And we have assigned opacities to them, so they show up, but we don't really want to see them. So what we can do is we make them transparent. We can do that by simply clicking somewhere here, creating a new control point, and dragging it down. And this means now we have made all the values from 0 to around 30 completely transparent, and they're gone from here. And we already see our head a little bit, because all the other values from 30 starting to 255 are with increasing opacity displayed now. And that's actually a good way also to look at the data quickly. That's what I often do when I get a volume data like this. I load the grayscale color map with this ramp opacity function. I create another control point here, and then I just drag it from left to right. So here I see essentially everything, and if I start dragging to the right, I see that the air around the skull goes away, and if I keep dragging, the skull will go away, and only the teeth remain. And if I keep dragging further, even the teeth go away, and we are left with a structure here, which is actually a tube, which has been inserted into the patient in order to make the CT scan show up better. Okay, so this is a nice way to look quickly, browse through your data, and we've seen that we essentially have 4 different objects here. We have this tube, we have the teeth, and we have the skull, and then we have the air around the skull, which we are probably not interested in. But anyway, so one thing we can do here now is we can try to actually simulate the isosurface that we have been computed previously. Because I know that the ISO value was at 56, so if I drag this to slightly before 56, then I create another control point here and drag it up to here approximately, then we see almost exactly the skull again, because what we have done is we've mapped all the values below 53 here, and see from 0 to 53 to 0 opacity, so they're invisible, they're not there. And then we have mapped all the values from 53 to 255 to completely opaque, so you completely display them. So it looks almost like the skull again. And you can actually compare that to our isosurface. That's why I kept it. And there's a nice feature in Avizo that you can actually split your screen and show two screens. Actually, we're already seeing our skull. What's also happened is, if you look closely here at your modules now, these display orange boxes, they're larger here, is now split into 2. So you can control which module you see in which of these displays. And so I have selected the volume rendering. I only want it on the left side, so I disable it on the right side. And on the right side, I actually only want the isosurface. So we keep the surface view, which is already on the right side, but I'll turn off the slice. We don't display it at all. Turn it off. Okay, so if you look at that, that looks similar. It looks slightly different. The reason is that this looks a bit noisy, so let's try to make that a bit better. One thing is, in the volume rendering, we have shading set to none. Shading means take lighting conditions into account, and not using any lighting doesn't usually look very good. So we might want to use something like diffuse. Now it looks already a bit more 3D, or even specular, meaning use also highlights, and then you see that actually it is. It looks slightly different because the colors are a bit different, but you essentially see the same as on the isosurface. Okay, so but we can do more in volume rendering. So let's go back to only the volume rendering, and I'm seeing the wrong thing, so I'm gonna disable the surface view and enable also displaying the isosurface. Let's disable that one too, and enable the volume rendering again. Okay, so we are now back here at this volume rendering. We have said before that we actually found 3 different materials that we might be interested: skull, teeth, and this tube. So we can use this histogram to this transfer function now to actually try to see these 3 different structures separately. So we can do it the following way. We actually have created a control point here accidentally. You can actually delete it by clicking with the right mouse button. It goes away. Let's start by trying to get only the tube. This means we knew this was the large values, so we just drag our control points to the very right. Now we only see the tube. But I don't want it in white, I want it in, let's say, blue, so I double click this one, I get a color pick, and I click blue. Now it's blue with a little white because it's interpolated. Maybe the end color is also white. Now it's more blue, but it's also interpolated. But anyway, you see a little bit of white still, but it's essentially blue. So we want to add the teeth. So the teeth are approximately here. I create 3 control points, drag them down, and here I see the teeth. Actually, I can make 4 control points because I know there will be a region which corresponds to the teeth. Let's see how far we can go. This is not enough. Maybe this one more to the left. There are the teeth. There are the teeth coming. Okay, that's probably too much. Let's make them opaque. And here you see the teeth. And they're white because we are interpolating from blue to white to black. That's actually okay. I will nevertheless create a new a new color control point here and make it completely white, so that we will have only white on the teeth. Now I need this one more bluish. Okay, that's too far to the left. Don't need that much here. Here we get it bluish. All right. Okay. Now let's add the skull. The skull was approximately here. I add a few other control points for the skull, and I want this one to be actually, let's say, a red. And another. And here now you see, let's make it a bit more transparent, maybe. And here now you see that you have all the 3 different objects at once in different colors. So that's what you can do with a transfer function. We have also seen it's a bit tedious. It's not perfect. You see that it's not completely blue. You might want to play around with the transfer function more to get a better display, but this can be tedious. And yeah, you have to play around with it and see what you can do. But let's take a quick look at what we can do with the Watershed module, what we can do more. So actually, I have done everything in the volume rendering model that we can do. So this is a nice a module that with little work you can get nice volume renderings. Let's try the other volume rendering module, volume rendering. I go to display volume rendering and create it. And now we see we have a similar problem that we have this stupid transfer function which doesn't really show anything, but we still have our grayscale which we modified, and this is still the modified version. So if I just select it, I have now exactly the same transfer function as I had for the Watershed module, and you see that it looks similar but actually slightly different. We can do the same trick again and try to compare we only want the volume rendering on the right and the Watershed is on the left. Perfect. So you see it looks similar, but slightly different. And the reason is, let me turn it off again. you have more options in the volume renderer than in the volume module. All right, so this means you have two different volume rendering modules, and which one to use? This depends. Volume is easier to take a quick look at what you want to do. You can actually get if you hit this help button here on the module help, you get a help for each of these modules, and there is it's in the other one. It's in the Valren help. There's a link to comparisons with the volume rendering module. And if you look through, so you have a table here, Valren and volume rendering, what you can do. If you look through that, mostly the volume rendering has more lighting effects, which might not be that important. The Valren has these nice, easy to use modes, which the volume rendering doesn't have. But the volume rendering module has the big advantage that it supports larger than main memory data. So if your data is really large, like say a few hundred gigabytes to terabytes, and it doesn't even fit in your main memory anymore, then you cannot use the Valren module, it won't work. The volume rendering module will work. You have to convert the data into a specific format, but you can really visualize very large data. We don't need that to do today, so we just use the Valren module to look at our data. Like this, yes, and that's what the volume rendering is. Again, play around, try to get used to what you can do with it, and happy exploring your data. It's volume rendering, and you've seen it's a nice way to quickly look at your data to get a complete overview, almost or as complete as possible, probably, of what's in your data, and you're going to use them. Also in the segmentation session, then to actually look at the data before we try to segment it. But it can also be tedious and you know can take a long time until you come up with a nice transfer function that actually shows you nicely what's in your data. But it's a nice way to quickly explore it and get an idea. All right. Anyway, this is the first session on volume visualization. I don't see any questions, so I would say we just take a short break. All right, so welcome back, everyone, to the second session in this introduction to scientific visualization with Avizo workshop. We're going to look at volume segmentation now, and actually we're going to use the techniques we have learned. We've looked at in the previous session, and to get a first idea, and then we'll try to identify the interesting structures in another data set. I'll just start the first video. And share the screen. So let's do some volume segmentation. So volume segmentation is the process of partitioning a volume into multiple segments, like just sets of voxels, or you can think of them actually of objects that are inside your data. And if you look at this the example here on this slide, this is actually an electron microscope scan of a tiny part of a rat's brain. This has been published about 2 years ago by people here working at KAUST. They took a lot of work, a long time to actually segment this volume. It takes quite some domain expertise to understand what the data really represents and what the actual objects are in there. And that's what the volume segmentation actually is about, to reduce simplify the volume to something that is more meaningful and easier to analyze. And in the end, it means that you want to assign a label to every voxel in a volume. So the original volume is probably given as a grayscale, lots of different values. And in the end, you want to have just a few values, like the number of objects you have in the volume. And that's what you do when you segment the volume. So we are going to use a data set which has been provided by Jamal Al-Amri from the Ali Al-Naimi Petroleum Engineering Research Center, or MPAC, here at KAUST. And it's also this is a CT scan of a mini core block isolated inside a shrink tube. And the rock inside the tube represents a sandstone. which is a type of rock found in oil and gas reservoirs. And the data set is given as 466 PNG images with a resolution of 742 times 742. And you see one of those images here. And if you look at it, again, you have the range of all kinds of gray values. But essentially, you see these three objects, so actually the two objects and surrounded by air. You clearly see the tube around the rock. And so that's what we're going to try to segment, to find in the volume. We start by taking a look at the volume using the techniques we have done before, try to understand better also in 3D what's going on, and start with some simple thresholding to do some segmentation. All right, so let's look first at the data. Let's open it. I'm here in my data sets in a stack directory where I have all these images. So I just press Ctrl A to select all of them and open them. So now we have 466 files. I actually know the voxel size here is 14.6397 in X direction. And this is in micrometers, actually, 14.6397 also in Y direction. And in Z direction, we have 14.63. So this comes from the specifications of, in this case, of the CD scanner. And that's what you should know when you get your data set, let's say, from the imaging core lab. In this case, I know this. It's just almost cubically, so that's actually good, but not completely. So we just load this. And here we have our data set. Quick look again. Everything is as we specified. And we can actually start looking at this data set now with the techniques we have done before to get an idea what's in there, what's the data like, what do we want to see, what do we want to extract. And the first thing is I still have them here in my favorites. I just like take a look at an auto slice. Turn off the frame. Okay, so that's the data set. There seems to be, we zoom in a little bit, a tube around these rocks, and this seems to be the air outside. So we might be interested in this tube and the rocks inside. Let's try a different slicing direction. So here we see it from the side, the tube here, and the rocks inside. From the other slice direction, that looks similar. Okay, so that's a first. Of course, you can browse through it to see what it looks like. Okay, there seems to be nothing at the bottom. Then we start having rocks and they pile up until the top. Here, similarly, from the side, you see the rocks. Okay. Again, it's not so easy to really visualize what it looks like in 3D, but we know how to do that. I still have my vol run here for fast and easy volume rendering. Let's take a quick look. Select the data set and hit vol run. Okay, so the direct volume rendering is not very helpful, especially with this transfer function, but we could change that now. And the easy way is now to just use these easy modes to look at it. So here we have maximum intensity projection, and there you see the rocks. So that's what it looks like in 3D. And actually, there is a few things we can actually change here in the transfer function. So you could change the transfer function, but it doesn't do anything in the for the MIP. So that's actually pointless here, but you can change the range. So here we have Avizo automatically detected a short range, which it thinks we don't want to see, which it detects as exterior. And actually, that's a bit too much in this case. So if we go a bit to the left with that one, we see actually the tube appearing. If we go to the complete to zero, this is the air, that's too much. But around here, 18, I think, around here, yeah, so you also see the tube. So you see the tube, the rocks inside. And now you might start asking questions and what do you want to do with it. So the first thing that we could do is we could try to compute the volume of the tube inside, and then try to extract the rocks and ask questions like what's the ratio of air to rock inside this tube, for example. Or you might even want to count all these little rocks. So there are plenty of questions you can ask about this, and to answer them, you usually have to now actually segment this volume. So let's start doing that. The first thing, if you want to do that, is let's turn it off the wall then. So you have if you have a volume like this, there is a group called the image segmentation, and you have actually a bunch of different modules there, and thresholding. And we look at thresholding first. Thresholding is the simplest segmentation technique, so simple that some people might not even call it segmentation, but it's here on the binarization, because that's what thresholding does. It just says below a certain threshold, it's not an object. Above the certain threshold, it is the object. So it just binarizes everything. And so we have, even in this binarization, we have a bunch of different thresholding techniques. And the first one to get a feeling for it is actually a good idea to use is interactive thresholding. Just do this interactively and see what happens. So let's create this one. So this one is actually, it is a compute module, but it has this preview type here. So although it's a compute module, it actually displays something. If you turn it off, display doesn't display anything, but you can display it here. The 2D slice, you can align that, and let's zoom in a little bit. Unfortunately, you cannot turn off the frame here. So we keep this orange. Okay. So here what you see now is the following. So first we have the same preview types, X, Y, X, Z, and Y, Z directions. We're looking at the X, Z direction. We have a color map, and we show the whole range. You can change the color map here and it makes a difference, but only on the image, not on these things. This blue stuff we see here, we go back to grayscale. The blue stuff is actually what we have now thresholded. So in this intensity range here, everything between 32 and 255 is displayed with this color mask, which is blue. You can change that. I actually like this blue, so I just keep it. You can also change the slice and go through it. So what you see, again, Avizo put some default numbers in there, automatically computed numbers, which aren't that bad, actually. You see it's already somehow just selecting the rocks inside. But anyway, it's a good idea here, the same thing, to you can adjust the range to the whole range, data min max. Then everything is blue, of course, because we only have values between 0 and 255, and we are selecting all of them. But now again, you can take this, for example, on the left side and start dragging it and see what happens. So the first thing to go is again the air around the tube, and then we see the tube go away and the rocks remain. And the interesting thing here is actually that there are a few very high intensity rocks, which we might want to segment in addition. So that's what you can here easily see. Let's try this this range of the rocks. Let's take a quick look at the 3D preview. This looks now actually has a display in 3D, and you see that that you're essentially getting the rocks. We have some artifacts down here, but also probably some of the air between the rocks. They're all completely connected, so it's a good start, but it's not perfect yet. But anyway, let's try to separate these. Again, we have a few different structures in there which you might be interested in: high intensity rocks, regular rocks, let's call them, and the tube essentially. So let's try to find good thresholds for them. Let's go back to the 2D preview for that. Let's go back to the correct orientation. So probably one hint that you have is actually here, the histogram. So you see 3 peaks of the histogram essentially, and then not a lot. So again, we don't have many high intensity voxels, and you see that here, although we have we're only displaying things where we don't see anything in the histogram, there are a few things marked. So these high intensities seem to be beyond this first peak. The first peak seems to be the rocks. So let's select the first threshold just behind this peak. Let's make it something like 78. The next threshold might probably is right in between these peaks. So these are the rocks. Now I can actually change my range on the upper threshold to 78. Easiest to just type that if you know it. Now we see that that we are not selecting these high intensity rocks, but we're also losing some region, I would say, which we actually wanted to be rocks. But yeah, that's the problem with thresholding. You'll see it in a second. It gets even worse with the tube. So let's keep, or maybe we can fill in a few. Maybe I'm just too far on the left. So that's, now we're getting more connected, but we're filling the holes. So you see the problem. Let's try to find a good one where it's mostly the holes are mostly filled. Let's say 34. So this seems to be the rocks between 34 and 78. And let's try to get the tube. So we move this actually further left. The other thing, you see the tube appear. Let's move a bit further. The tube fills. That's maybe too much. We already have a few pixels outside. That's too much. 19, let's try 18. That's a bit better. Let's try 18, and let's go to 34 here. That was what we said is our threshold for the rocks, and the problem you see, maybe 34 is too much. Let's try 33, that doesn't change much. You see the problem is that we cannot really separate only the tube by thresholding. It's just the intensities inside overlap with the intensities of the tube. So we just cannot separate them. You can try play around with these values, find the slightly better ones, but you will not be able to separate the tube completely from everything else by just thresholding. But anyway, let's. So now we have found a few thresholds that look interesting. Let's take a look at this tube now. So we have done this. We have the range. Now we can actually hit apply. Let's see what happens. If you hit apply, we get another data object. And if you look at this data object and compare it to our original object, you will notice that it has exactly the same resolution, the same physical size, the same voxel size, because we just replaced the actual values of our data with now just 0 and 1. And you see that here, the thing that changed is the data info. First, it says now label binary. It's still an 8-bit unsigned, but we only have 2 values, 0 and 1. So everything not blue is 0, and everything blue is 1 now. And the important thing is that it's actually the data info changed, although it's the same. It's also 8-bit unsigned on the same grid. So we have exactly the same memory consumption for this. It's just a different data type, and that's important for Avizo to know, because it's not volume data anymore. It's actually a segmentation mask, a label mask, the label volume. Okay. So we have this data object now. You can now, of course, save this to disk. If this took a long time to compute or was very tedious to manually segment things, then you might want to save it out. We're not going to do this now. Let's take a look. We can now actually try to take a look at this one. So we turn off the interactive thresholding, which has just previews anyway. And there's a nice module for which is rather useful for this kind of label volumes, which is in the display at the end. It's called voxelized rendering. This is useful for this kind of label data. Let's take a look at that. You see immediately what happens. We're now actually really just displaying the voxels as little cubes. Looks a bit like a Lego model, but that's essentially what it is. So each voxel in the volume, which is a little cube, is displayed if it has one, or not. It's transparent if it's zero. So we see this tube. Let's zoom out a little bit. So the tube is nicely here. That looks good, but the inside is not what we expected. So we have a lot of stuff inside which we actually would like to get rid of, but we cannot do this with thresholding. All right. There is another there's another interesting module for this kind of label volumes, is that again that you know, just displaying this this voxel representation of the volume, you might want to actually again extract this as a surface to process in other programs, so just for a nicer display. And you can do that in this label volume. You go to compute and say generate surface. There are a bunch of different things to do, but generate surface is a good module to actually generate a surface. You can do some smoothing, can play around how much you want to smooth it, but in principle you can just say apply. Let's hit apply. Now Avizo warns us that this will actually generate a rather large surface. I think it's a bit overcautious here. It's not that large, but it will take a few. So we can continue. It will take a few seconds. You see it's smoothing the labels. Then it starts generating the triangles, building the triangles, and now it's done in a second. There it is, and we have another display module and another data object, which is now actually a triangle mesh. You see it here. It's a surface mesh. This number of points, number of faces. If you turn off the voxelized rendering and take a look at this, we've done that before. You can actually just take a surface view. I still have it here. Look at the surface view. All right, now I've done two. Don't want that one. A second. Okay. Surface view. So you see, it looks smoother because we smoothed a little bit. It looks a bit better, but it looks also different inside because of the smoothing. We have lost some structures inside. And if you look at them, again, we have the surface view default options of the triangle normals. We want the vertex normals, and now it looks smoother. All right, so that's a way to look at this extracted object now as a triangle mesh, as a surface. And again, you could save it now out by here. Save or export. Okay. Now we had three different objects in there. We also had two different kinds of rocks. So if you want to do that, if you want to look at all of them, you could now do another interactive thresholding on this and generate the rocks only. But there's an easier and faster way to do that in one step, and this is called the interactive thresholding, multi-thresholding. It's again in segmentation, and it's also actually already here, multi-thresholding. If you create this, let's move it down. We see it down here. So what you can do is you can specify some regions, and by default you have two regions, exterior and range 1. Let's give it some nice names. Let's call our range 1 cube. And separating by space, we can now add actually more ranges like rock. I call it rock 1 and rock 2. And if you do that, you see that you get these labels now, these properties to specify actually the thresholds between the exterior and the tube, which we said before was around 18, between the tube and the rock, which was around 33, and between the two types of rocks, the lower intensity and high intensity rocks, it was about 78. Okay, and if you compute this now, what you see is so we've got again another data object with the same resolution, everything the same, but it's again a label volume, and we actually have now 4 different values in there from 0 to 3. If you look at that in the voxelized rendering, still have it here. This is not showing everything because I changed already the transfer function. Let's go to the voxelized rendering. Change the color map, make it completely opaque. Okay, so here you see now all your objects. In light blue is the tube. So we again see that we have more stuff selected inside. Dark blue are the rocks, and red are the high density rocks. If you want to look at them separately, you can do this here by changing the transfer function, opacities of the transfer functions. I'm showing opaque, I'm showing everything, but I can use this band pass, for example, to move a region around. So if I just want to see my high intensity rocks, I move this band pass region around the red stuff. Now you see only the small rocks inside. If I want to see also the high lower intensity rocks, I can move it here. Now you see both of them. Only the rocks. If I want to see only the low intensity rocks, I move the box over the blue region, and now the red boxes are gone. So you can just volume render this now and use this the transfer function to actually look at the individual objects. All right, so this is what it looks like. Let's make it completely opaque again. If you do just thresholding, so you see that that it's not good enough. We cannot do exactly what we want. We get the tube from the outside nicely, but we cannot separate the inside from the tube. And the rocks might not be exactly how we want them. We might have them probably separately. There's a small one inside here, which is also maybe not what we want. So thresholding is just too simple, but it's actually usually a good first step, and use this as an input to segmentation algorithms. All right. So that was yeah. So thresholding is it's just always the most likely the first step you're going to do when you segment something just to see if it works. If it works, perfect. But with most real world data, it's too simple. There was a question in the chat. Let me answer that first. So what happens if you enter the wrong dimensions? So first, generally, when you import your data and you enter something wrong, usually something will go wrong. But it depends on exactly what you do. The good thing about the way we loaded these data sets here, which are just PNG images, a stack of PNG images, the PNG images have all the information about the data actually in them already, so that cannot go wrong. That will always work. But what you could do wrong is to enter the spacings, the distance between X, Y, and Z directions, and I guess that's what you meant. That you could enter some wrong numbers there. And the good news there is it will look different. That's the problem. It will not be completely wrong. It just depends on how much different numbers you put in. But let's say you have so in our case, the X and Y distance was the same. If you would specify a x distance twice as large as the y distance, for example, then the tube would just look like an ellipse from the top than a circle. So it will just scale differently, and things might look squashed or stretched out. A little bit distorted often. So in this case, if I just put 1, 1, 1 in there, not much would have changed. You probably wouldn't even see it because the three distances are so similar anyway. But you might want to put the real numbers in there if you know them, because we'll see later that we can do measurements and if you make a measurements, you will get your measurements in the correct unit already, and in the correct and you will get the correct measurements. If you put in the wrong numbers, the wrong spacings, then your measurements will be wrong. Okay, I hope that answers your question. So the best way is, I mean, you just want to put in the right numbers, and you should usually know those numbers because you got the data from somewhere. Someone gave it to you, or you created it yourself. That you should just know those numbers. Okay, let's continue with the segmentation. So thresholding is not good enough, but we can use it actually as an input to other segmentation algorithms, and the one we're going to look at is called the Watershed algorithm. And I'm just gonna start that one now. And share the screen. There we go. All right. So the one segmentation algorithm we're going to look at is called the Watershed algorithm, and the name comes from an analogy to situations like you see here on the left, where you have a little valley, and there are all kinds of objects in there, even a small city. But if you imagine now that the valley would be flooded, the water would rise, it would essentially cover all the small details in the valley, and what you would end up with is essentially a lake, one object. And then if you have these watershed divides, and the valley on the left would flood as well, you would again ignore all the small details and get just another lake or an object, a segmentation object. So on the right you see a 1D stylized figure of that. So in order for this algorithm to work, we have to essentially provide the watersheds and the basins. And then we will also have to specify where to start the flooding. This usually is done, you start with your original volume, and then you compute the image gradient, and that, of course, Avizo can do. And we just use this image gradient then as watersheds and basins. And then if you have the markers, in this case, which are then called markers, the markers are the places where you start the flooding. In this case here, they are just given. Let's assume we have them. Then you can run the watershed algorithm, and it will start from those markers, flooding in the areas that are bounded by the watersheds. And then you end up with a segmentation image like on the right. So the one thing we have to provide to the algorithm is those markers. And one way how to do that is to use thresholding. Let's just take a look at Avizo, how to do that. So let's take a look at the watershed algorithm. So here I have our data. Let's just quickly again look at an author slice. We know what it looks like. But we want to essentially get the tube, get maybe the rocks. And the watershed algorithms uses the gradient magnitude of the volume data to separate the regions. So a good idea to get the feeling of how this works is to just compute the gradient magnitude image for this volume. And you can do this by going to compute, say gradient, and create the gradient. I would change here the output to float, so we have a bit more resolution, and just compute this. Hit apply. Takes a little, and then we have another data object, which is our gradient. The gradient is, however, a vector. So it's still in its three components. In order to see the gradient magnitude, we compute its magnitude. So we go to, again, compute and say magnitude. Okay, now we have magnitude. And here our magnitude is now again a grayscale image of the gradient magnitude. Let's take a look. Let's see how it looks like. So this is the author slice now of the gradient magnitude. We zoom in, we see actually that the gradient magnitude somehow nicely outline the regions we are interested in. We can increase the view a little bit by moving the slider here so that we get brighter lines. If you do that, stop here. you see actually that first we get nicely the tube outside, so this should work nice, nothing should flow over here. And then we get maybe the rocks, maybe not the separate rocks, but somehow the rocks in the inside, maybe we get some problem here with the tube, and maybe down here, but it could probably work by using the gradient magnitude if you start flowing from the tube from here and from the rocks inside, from the air outside. So that might work. So let's see how the watershed algorithm works. So you have a simple way to do that in Avizo is to use a module which is in image segmentation, and it's called watershed segmentation. If you create this one, first thing you see, it's blue. It is blue because it's actually, and you see that if you select it here, it's actually a script file. So that's also a nice thing in Avizo. You can actually write your own scripts to implement your own algorithms using modules of Avizo, and that's what this script does. You can actually take a look. There are quite a lot of scripts. Here's our water segmentation. You could take a look at the script and see how it works. However, we don't have to do that. We just want to use it. So again, we can browse through our data, and we now know what it looks like. And now what we can do is we have to tell Avizo how many faces we have. Here it's called faces. That's essentially what the objects in our data. And we have 4. We have air, we have the tube, we have rock, lower density rock, and then higher density rock. So we say 4 faces. And then we go to the next step of the algorithm. So this module nicely leads you through the algorithm by step. You just say apply. You get to the next step. The next step is that it wants to compute the gradient magnitude image. Now it does that for us. There's nothing we have to do. We just say apply to compute the gradient magnitude. It takes a few seconds. And when it's done, we have the gradient magnitude image. We don't see it because it's hidden in the algorithm. So we don't get actually a module for this gradient image, but it's now computed. And we are at the next step, step 3 of 8. This step says threshold the gradient magnitude. So we also do some thresholding of the gradient magnitude, nothing to specify there. So we just hit apply. And it's done thresholding. It opens a table view that doesn't show anything. So we just close it. Okay, so the next step, step 4, is threshold phase 0. So that's how we do it now in the watershed. Essentially, we have to give the watershed the markers to start the flooding. And phase 0 means give the markers for phase 0 for the air. So we just do it by threshold. We threshold the air. We know it's around, let's say, 16, maybe 17 or 18. So the blue stuff again is the air. We see we have everything selected outside with not move spilling over here. And we have air in. There are some pixels here, so maybe I go back to even 15 to be a bit conservative. So this means the air, to create the air, segmentation of the air, it will start flooding at all the blue locations. So outside there won't be any problem. And then it will start flooding also from the inside here and see how far it gets with relation to the gradient magnitude image now. So this is the air. Let's go to the next phase. This is now step 5, and we now want to segment the GIF markers for the tube. And we know the tube is approximately, now we can again be a bit more conservative. Here it doesn't matter if you have holes in the tube because they will be filled by the watershed algorithm. The problem is again, however, that we cannot get rid of all the blue stuff inside the tube, but we can try. That's too much, something like that. So these are now the markers for the tube. So we see that we should get the tube, but we again might possibly get more regions here than we want. And the problem again is by simple thresholding this, we cannot separate these regions from these regions. So, but anyway, let's go with that for now. Let's go to the next step. Step 6. is our low intensity rocks. Again, we can be conservative. We don't have to, if you have a few holes, that's no problem, but we want to stay below the high intensity rocks, which is around 78. Let's say here. All right, hit apply. And finally, we go to the high intensity rocks. So this is almost correct. I make it a bit conservative again, a bit over 78. 78. That's too much. Let's do it manually then. Let's make it 79. And hit apply. And now we are already done. It says step 8 of 8, compute the watershed. So we do that. And it will start computing. That takes a few seconds. It's now doing the watershed. Going through the planes, you have a little bit of a progress bar, which is, as usual, not very helpful. But here's the result. So we see the result is called basins now for the watershed. Again, if you look at the information, it's the same as before, same resolution, same physical extent, but now it's a 16-bit unsigned. I think you cannot change that. And we have only 4 numbers in there, 1 to 4. And we see them here. And this is again a volume. We can take a look at the voxelized rendering, say. So turn off this preview. Select the basins, do a voxelized rendering. Again, I have my color map already set up that it's only showing the tube. But let's go back to edit the color map to show all. Let's do it opaque. Here now we see everything. We also have selected the air, so we see the block around it, and the tube and the rocks inside. So we see we have some air inside, more air than before. But if we look at only individual objects with our bandpass opacity, so these are now the high intensity rocks. Now they're green because we have one more object here for the air, but they look similar. Only the rocks are now in red and green. And if you look at the tube, again from the outside, it looks okay. It looks like we got it, but you see already here. First of all, we missed something here, so we probably can fix that by doing a better thresholding for the markers. But we also see that we have stuff inside. And this is actually the big problem. Even with the watershed, we do not get rid of the stuff inside. Let me just remove the rocks to see them. So you see there are fewer things inside now than before, but it's still stuff there. We cannot really get rid of the things inside because by thresholding, we cannot separate the tube from the inside, and even the markers will start flooding from the inside, so we get some structures inside. So this is the simple way to do thresholding, and the problem is to watersheding, and the problem is if you do it only with thresholding, you might not be able to create markers the way you want to. So we're going to take a look at how to do this in a better way in the next section. All right, so that was a first introduction to the Watershed algorithm and using only modules that are available in Avizo. And you are, as you've seen, just led through the algorithm step by step by this module. So it's actually quick and easy to use, but you have the problem. You have to specify the markers for the Watershed algorithm to where to start the flooding, and depending on if you start flooding at the wrong location where you don't want to have the tube, for example, then you will get tube there, and that's not what you want. So there might be a lot of different ways to do to specify these markers in a better way. And one of them is to just do it manually in the segmentation editor. And it's probably a good idea to look at the segmentation editor of Avizo anyway. So that's what we are going to do in the next video. Let me share the screen. Okay, so we've seen that watersheding with simple thresholding is also not good enough. And essentially the problem is that this tube is just stubborn. It overlaps with intensities inside. The air outside works nicely. The rocks work somehow, but the tube is a problem. And we can actually try to improve that by just not using thresholding for the tube, but essentially specifying that the markers, giving the markers manually to the watershed algorithm. And a way to do that is what is called using a segmentation editor. So you have this here as a tab called segmentation. I still have my old project here. So we did this watershed, we created the basins. If you go to the segmentation editor, it opens a new view where you see your already a 4-split view of the data. And here's a 3D preview, just showing the axis-aligned slices. And what we're seeing here is one of the data objects that we have created during the watershed algorithm before. That's a possible label field for this segmentation editor, but it's not the one we want. We definitely don't want the gradient magnitude thresholded. And we see we have created quite a few data objects when doing this watershed algorithm, and the final result were the basins. So we can just select the basins here, and we see essentially again our the labels that we created with this script watershed algorithm. And here we see our 4 materials. They are called material 1 to 4. We couldn't give any names to them. But here's actually also a nice way to quickly preview things, because you can display them here in 3D. Material 2 was our tube. So here we see our tube again, and we see that we have a lot of stuff inside. But anyway, I don't want to work on this basins that we've created. I want to actually create a new label field. So I say new here, and Avizo asks me for a name, and the default is just to use the name of the data object .labels. I keep that, and so we get an empty label volume now essentially, we see our materials here. So we can specify how many materials we want. We just use the first one, and we call it, so the exterior is not used. We call it the air outside. We say rename and call it air. And then we add a material here and make it a tube. This is just a name, but just for us to know what we want it to be. And then we add more. We can add as many materials as we want. Now, to make it a bit faster, I just create one material for the rock. So just keep the low and high intensity rocks in one material for now. So now what we want to do is we want to create the markers for the watershed algorithm. We saw that for the air and for the rocks that actually work with thresholding, and we can do that here as well. So you see here is a list of algorithms you can now do to select voxels for the different materials. So we say, for example, we select the air, and we have a thresholding. This is thresholding. Module or way here to do thresholding. This is exactly the same, and we know that the air was, so we see in blue the selection and the slices. We can play around again, but we know that 16 here, this would be too much. We get the tube that 16 approximately was fine for the air. So let's just keep 16. and say select the masked boxes. So for now, these blue things is only masked. We want to select them actually. We select them, now we see the color changed, and we have them selected. And now we want to add, here you have ways, things you can do with the selection. We actually want to add this selection to the current material, which is the air, which we have selected here. We add it to the air. So now you see in this way saying that we have actually assigned material to the air, and we can look at it by looking at it actually. So we see, turning it on in 3D, we see that we have selected quite some nice air around everything. So that's good. Let's do the same with the rock. Let's turn it off here. We can actually manually also assign markers for the rock by just thresholding. So we do the same. We select the rock here. We go and select rock. We still have the threshold here selected, so we have the threshold. I go to the rock. I want to have everything above 33 now, all rocks. We can check here, the blue stuff is, we can actually unselect even the 2D display of the air so that we see better what we select for the rocks. This is the blue thing. So we can, it looks okay, like this again. And so that's fine. We can do that. And again, select the masked boxes and add them to the current material, but select the rock. We want to add them to the rock. To make sure we did the right thing, we can again quickly look in 3D at the rock, and these are the rocks. So that's okay. But now we want to get the tubes, and we cannot do that. We could here again do it manually with thresholding, but that as we have seen, does not work. So what we can do here now is actually do it completely manually by simply painting. So we have a paint module here, and we can, as in other paint programs, just select different brushes. So we select the brush, and we start painting where we want the tube to be. So I can paint in here. That's actually a bit small, so you can make it for now larger, and we just paint, let's say, once around that this is the tube that we want. All right, let's take another slice. Let's say here. Let's just do a few. I'll just do 2. Try not to hit the rock or the air. That's, oops. That's easier with a mouse than with the mouse pad here. Okay, let's keep it with this 2. Let's go back to the 4. Let's also do it for the other slices a few times. Let's make it big again. Can zoom in a little. That's easier. It's just these are just the markers where the watershed will start the spilling. So it can be very, very rough outline of where we want the tube to be. Let's take one more slice somewhere else. Make the tube here and here. Let's go back to the 4 views and do it once more in the other direction. Let's make it big. Zoom in a little and do it here. Okay, one more slice, maybe one over here. Let's mark the tube. And let's go back to the 4 views. Now we again say, this is now already selected. So we just say, add the selection to the current material. We have the tube selected here. We add it. You see the color changes, it's added. You can actually look at it in 3D. We'll see it doesn't look like the tube yet because we have just selected these few circles and lines. But now we can actually use this for the watershed algorithm. So these are the locations where the watershed will start, and we use the other regions for the air and the rock as created with the thresholding. So to do the watershed, you select it here. It's called watershed. For first thing, again, what we have to do is to create a new gradient image. We just click this, and it will compute the gradient image. Again, we won't see it because we don't need it. And it's done. And then it asks for the markers, and we actually want all the materials, so the selected materials, and select all of them. So you see that here they are selected as markers. You can select them manually or just press here, select all. And then you're actually ready to do the watersheding. Just click apply and create a new label field. Now it's working. Doing the watershedding, again, takes a few seconds. And that's what it's done. We already see only the tube here because I've only selected the tube here. I can take a look at the rock. The rock sits nicely inside. And the air is around. We're not interested in the air anyway. That's what it looks like. And you see it's not perfect. Of course, we're missing things. So the way to fix this is now to go to those slices where there's nothing there and paint a few things again and go through that a few times until you have the whole tube. And if you look at it inside, it's really only the tube now. So that's how you create this label field. And if you go back to the project, you actually see that we have, this is already a lot of things here, but we have actually created our labels somewhere here. They are now it's just a module attached to our data thing, and this is, as you see, again, same grid, the 8-bit unsigned label with four objects inside. If I disable this one and do a voxelized rendering, still have it here. You see that it's still the old label because this is the wrong label field. It's actually this one. Labels 2. The label 1 is the one that we actually created first, and label 2 is that one that the watershed algorithm created. So here you see your tube. Again, you have a few holes to the left. You could fill them. Do this iteratively until you create your segmentation, and you only get the tube here when you're finished, which is just not possible by only using thresholding. All right, so that's that's how you use the segmentation editor in 20 minutes. There's of course much more to it, and you can look at the help and get an idea of what you can do with it. And you've seen how the watershed algorithm works, so it's a bit better than thresholding because it does not just look at individual values. I just want to add that it's usually, especially, so it works nicely on these kind of data, which is a CT scan. CT scans are usually not that noisy. But if you have other data, especially from electron microscopes, they tend to be very, very noisy and have other different artifacts like different lighting conditions at different parts of the image and volume. Then even a watershed might not be good enough, and you will need more advanced algorithms. And one way to start looking into this is to go and attend our workshop on Thursday. All right. If there are no questions to this, I would say there are no. I would say I will make a quick break again. All right, so welcome back to this last session of the Intro to Visualization with Avizo workshop. So we have, so the idea of this workshop was to give you a hands-on introduction to how to use Avizo, how to use visualization techniques, by just showing them to you, and you can then explore further. And now I collected a few topics which I think are just interesting for overall views of Avizo. And the first one is actually good, very, in my opinion, rather important things to know how to save and use projects in Avizo. So I'll just start that video and share the screen. I want to talk a little bit about project management in Avizo. So you can save your projects and load them at a later time again, like in other programs like Word. You save your document, you open it again, save, keep working, save again, save often, not to lose your data. You can do the same in Avizo, of course, but there are a few differences. The main reason is that Avizo is a data visualization tool to visualize scientific data, and scientific data can become rather large, and there's no single best way how to handle this. So Avizo essentially presents 3 ways to save your projects. The third one is a little bit hidden, but extremely useful. But let's start with the first 2, the default ways to save your project. In order to do that, I have created a simple project. I've loaded the Scalar dataset, created an isosurface, extracted the surface, and then displaying it in a surface. So I want to save that to disk and load it again. Let's just try that. The first thing, so you do this on the file. The first thing is you have, as in most programs, the options between save projects, so save over the same project file, or save project as. Save project alone in Avizo is really dangerous to use, especially if you use a shortcut Ctrl+Shift+S. You work on something, you press Ctrl+Shift+S. Avizo will just overwrite the project file and not even notify you that it has done that. You can quite easily accidentally overwrite a project file you still might want to use. But it can also be rather useful if you know you're working on something with a lot of small steps and you always want to make sure that the project file is up to date. Just press Ctrl+Shift+S all the time. But you have to know that. And so it's safer to actually always use save project as if you want to make sure you're creating a new project. So let's do that. The first thing we get is now this choice between these 2 ways to save the project. The first one is minimize project size, and the second one is minimize project complication. So let's try just the first one, minimize project size, only necessary data is saved to disk. Let's do that. I have actually created its own folder where I want to save my files. Already saved one. Let's do another one. Scal 2, and let's do that. Okay, that's done. So let's see how that works. So we can actually say new project, then we save remove anyway. We don't want to actually save this now, and we say open project. Let's see how that works. I just saved the Scal 2, so let's do this. Open the project, and there it is, it works. So that's nice. But let's take a quick look at what this file looks like, because we actually just have a text file. This is good. So it says, first of all, it has the extension HX, which is the extension for Avizo project files. So that's good to know. And they are just text files. So I can open them with a simple text editor. Let's just say Notepad on Windows here. And you see it's an Avizo project. You have the version of Avizo that has been created with. So you can just look at that. And that's often very convenient, especially. So you don't really have to understand the script here. It's not necessary, but there are some interesting things like this line here, load. Here it actually loads out our data set. This often happens that this fails because you might want to reorganize your hard drive, move things at different locations, and then Avizo will not find this file here anymore. Or you just want to rename it. You don't like this cal.raw.am. I like to keep this raw.am to know that this file actually has been just created from this one. But if you don't want to keep this, you of course can just rename it to cal.am. And if you do that, and then at some later time you want to keep working on this project, you forgot about it. If you try it, let's do this. Move everything and open project. Let's load the same one which just worked previously.
we get an error. And this error is actually not very informative. It just says error in script. But at least it tells you the line number and which line actually failed. And so it should be easy to think about that you might have renamed or moved this file to a different location. So of course you could now just move everything back, but maybe you don't want to do that. So an easy way, because this is just a text file, is go to your text file, go to this line and just fix the file name. In this case, it's just one file anyway. If you have a lot of data files to load, you can always do a find and replace. But here I can just delete this scald raw, make it as scald.am. I would leave this here as the label because this is the name that Avizo now uses later on to execute all these commands. So if you change this one here, you will have to change all of them here and maybe later on too. So I keep this, that's easier. But then you now just save your file and try to load the project, open the project again. It works again. So that's good. So this also often good to know that if you get some errors, especially from loading, you can actually just fix them easily in the project files. But let's take a look at the second way to save your project. Again, save project as. Now we choose to minimize project computation. All of the data of the project is saved to disk. Let's just press OK, and let's call it scald3. And save it. Now, actually, we get a message that we have unsaved data. You actually also see that here you have a little star as usual, that this data file, this data object actually has not been saved to disk yet. So you could save it somewhere where you want it, or in this case, it's pretty convenient to just say auto-saved. And Avizo will just save it for you. We do this. Let's see what happened. We go back to our directory. Go to the projects, save the project. Here is scald3, the project file again, but as in addition now I have a directory called scald3-files. And this is what Avizo does in this mode is it creates a directory, project name -files, where it saves your files. And here we have our extracted surface. So that's also good to know. And again, the scald3 is just a text file. We can look at it. Right, so we're just loading the scald, but we're loading the scald from this datasets directory, which I created myself. So if you scroll down to the isosurface, here it actually loads the isosurface, extracted surface from this scald3-files directory, which is in the script here, which is the directory where we have saved the project, which Avizo thinks of as a script. So if you now, for example, wanted to share your data with a friend, you just copy this HX file and this -files directory. Avizo, when your friend loads this project, Avizo will find the extracted surface, but it might not find the scald data set because it's in this datasets directory. Either you forgot about it or you have a lot of data which is lying around at different locations, and it's just tedious to keep track of them. That's the situation where you want to use the third way that Avizo provides to save a project. And let's just do that. We go to File, Save Project As. And now that's actually a bit weird because you could use it if you say minimize project size, but then it won't work. So you actually now have to select again minimize project computation. You say OK. But now in the save as type, here you have a second type, which is called Avizo project and data files pack and go. That's what we want. So we select this. Let's call it scald4 and save it. And if you look now in the project directory, you have your scald4.hx, you have your scald4-files, and in this directory now you have actually all the files you need to really load this Avizo project file. Essentially, for each load command in the project file, you have this corresponding file here. So if you want to share your data or move it somewhere else, that's a good thing to do. You just need to copy these two files now and zip them maybe and share them with whoever you want to. So So these are the ways to save your projects in Avizo. You have to think about yourself, which one is the one you use. Usually the second one is okay. You usually have enough space on your hard drive that you can save the computed files out, and then you don't have to recompute them every time you load the project file. But you have these two other options, and they are just good to know.
All right, so this is about saving projects. Happened to me a few times that I moved somewhere else and had to walk back to the office to get another file because I forgot to copy it. So if you use this third option, you always have all your data files. The second option is probably that what you usually want to just save your computed files, and you have this option. If you work with very large data, you probably want to use the minimize size option at some point. All right, so the next thing I wanted to talk about is, as I said in the beginning, we're going to touch on all the steps in this little workflow, and one was called preprocessing, filtering and preprocessing, and it just didn't fit anywhere else. So I just going to show you a few things about this here. Let me share the screen. Let's go.
So here's this overview of a typical workflow again, from data acquisition through import, filtering, and pre-processing, visualization, segmentation, measurements, and analysis to your final presentation. And we have looked in this workshop at the visualization and segmentation. I also want to talk a little bit about the filtering and pre-processing, which is a simple but rather important step and often overlooked. So let's take a quick look at a few techniques. All right, so I'm here in Avizo. I have loaded our data set of the rocks in the tube. And let's quickly take a look again. Attach an author slice. And actually, I also want a bounding box in this case. I know where it is. I changed the color. If you look at the data, so I've said that data sets for scientific visualization can become rather large. For this workshop, I've chosen a reasonably small one, but you might encounter much bigger ones. But you might not be interested in all of the data set, at least maybe not at once. And if you look at this one, we obviously have a lot of air around that tube and the rocks, which we actually don't really need. And another thing, if you look from the side, for example, change the slice actually. If you look from the side and browse through it, maybe you're not interested in the bottom here, it's upside down, but in the bottom of the tube here, where things might get more complicated. Maybe you just want to know what the average portion of this tube looks like. So you could just look at the lower part of this volume. And what you can do in this case is what's called extracting a subvolume. It's in if you select your data, go to compute, you have volume operations, and there you have a module called extract subvolume. If you create this, you get in blue this subvolume, which a region which is the region which you can extract. So you can move it around, just interactively actually. Look at it from all sides so that you understand where it is. And in this case, actually, it's better to change the projection to orthographic or parallel projection, not the perspective, because perspective here distorts things. And if you do the parallel projection, you really see it from the side. It's still in 3D, so the box is actually still there, but because it's now projected in parallel, if you look at it from one side, you really just see that one side. So you can actually easily now move your region somewhere, your box somewhere where you want it, like this. If you look at it from a different direction, it seems like the slice is gone, but it's not. It's just rotated out of view because it's really looking at it completely from the side. So we actually want to change the ortho slice, look at the other directions. Like here, for example, we actually want it to be somewhere here, probably. And just to check again, we did change something here, or I didn't put it where I wanted it. I actually wanted it around the tube. This looks okay, this looks okay. And from top, we just want it around the tube. So this is good. If you now, you could also specify this extents of this cropping volume manually, but we have done that interactively now. So these are the actual numbers. And we can now just apply this. And what we get is a new data object with view. And if you look now at for example, the resolution is smaller than the original one. And especially the memory size, this was 250 megabytes. Now it's less than 100 megabytes. So if you're interested, if you have parts in your data that you're actually not interested in, it's best to remove them to make your life as easy as possible. The smaller the data set, the easier it usually is to analyze and visualize. You might even be interested in, to start with, for example, do not do the whole thing, but just extract the rocks. So you might want to just take a first look at just what the typical rocks look like. And you could extract a subvolume like that. But there's actually, in this case, and probably also useful in other cases, a different way to do this. So I want to show that. Let me actually remove this one now. We won't need it anymore. And also the extract subvolume. So there is in the compute group in volume operations, there's another module, a useful one, which is called volume edit. So if you do this, the difference here is we're actually editing now the volume. And what I want to do is I want to actually essentially set everything completely to 0. Which I'm not interested in. And you can do this either by drawing here or by using again a box like that. But the nice thing in this model is you have different shapes. And you could, for example, use here a cylinder and align it with the z-axis. And then we can actually just select the rocks now in a cylindric shape. So from top, it looks like a circle. Maybe that's too much. Let's be a bit conservative, move inside like this. And let's look at it from the side again. Now we have to use these. And we have to use our ortho slice here. Okay, that looks okay. That looks okay. Maybe we move that a little bit in. This side, it looks okay. Actually, we can also, again, move it down here. We don't want the top part, just want this part maybe. Okay, that looks okay. So if you do that, select the volume edit. Now we cut it. We say cut the outside. We don't want the outside. We only want the inside. And what happens is after a few seconds, we get another data object. But this time it's still on the same resolution. So we still have the same memory consumption, but you already see in the preview, or if you attach a quick ortho slice to this one, that actually everything around our cylinder now is black because it's 0. And now you could even crop it further to reduce the memory size. And there's actually, in this case, now a simple way. You have here a crop editor, which also gives many more options. But an interesting thing is this auto crop here. Just say auto crop, and it fits the smallest box around your data that's not 0. So now that's exactly what we want, and we're there, and we're already seeing it on this slice. So we see the resolution has been reduced, and now the memory size is even just a bit more than 50 megabytes. So this might be, if you're just interested in the rocks, for example, be much easier now to just visualize and analyze the rocks. But this, again, is an important step. If you're just interested in certain parts of your data, just extract it. It makes your life much easier than if you have this large data set and you're actually not really looking at large parts of that data set. Okay, so another thing that I said before is that one of the problems is often that, let's remove this bounding box now, we don't need it anymore, if you look at this data, just keep this and work on this one now, that can be rather noisy. This is a CT scan, so it's not that bad actually, but it's still a little bit noisy. If you have data from an electron microscope, that the noise will be much worse. So one thing is that you could try to filter, smooth your data to make it easier to work with. This is of course also dangerous. You could change your data in a way that your measurements, your analysis afterwards gives different results. So you have to be careful and you have to know what you do. The good thing is in Avizo you can directly look at what the smoothing does and how it looks like, and if it looks reasonable or it's maybe too much. So you have a bunch of modules to do that, and they are in image processing. So you see you have a lot of filters in the edge detection filters. Here you have smoothing and denoising filters, you have sharpening filters, morphological operations, all kinds of things. And in these groups, again, a bunch of different types of filters, even in subcategories. Smoothing, there are lots of different filters, from Gaussian filter, simple median filter, to more advanced like a bilateral or non-local mean. So it's all there. Actually a good way to look at the most or a lot of them, how they work, is to use this filter sandbox. So if you select this filter sandbox and create it, what you get is, again, zoom out a little bit, you get a region of interest. This blue box, you can move it somewhere where you want it, maybe make it larger. And then, let's zoom it a bit more now again. And then you can choose a filter here, and you will get, you have a choice of a few ones here. And you get a fast preview within this region, and the outside it will not apply the filtering. So you actually have a nice way to compare how your filtered data looks in comparison to the original one. So here is a Gaussian filtering, simple smoothing filtering, which also smoothes over the edges, which is often not desired. So you could use some kinds of edge preserving filters like the bilateral filter that's a bit sharper, or anisotropic diffusion, rather similar, or a popular filter is actually non-local means, which really brings out the patches of your, in this case, the rocks quite nicely. But this is a rather expensive filter to use. So I will just, for demonstration, I will go back to a simple Gaussian filter, because if you now, if you're happy with that result, you say, okay, I want this now on the whole data set, you just say apply. Then Avizo applies it to the whole data set, and you get another data object with your filtered data. If you turn off the auto slice and the filter sandbox, which is here actually the preview, and attach a auto slice to this one, you see it's now completely filtered and completely smoothed. And there are lots of filters, and there are some parameters you can set. Of course, you can play around and try to pre-process your data in a way that it makes the visualization, maybe segmentation, easier. And when you then do the segmentation on this filtered data, I mean, all you get is another data object, which gives you the segmentation mask. You can then, of course, use this data object as a segmentation mask for your original data. So you've essentially just used the pre-processed and smooth filtered data to create the segmentation mask. But the segmentation mask then you can use to actually analyze your original data.
All right, so these are some simple, but I think rather important steps to do before you actually start the visualization and segmentation. And I want to stress that again, especially the extract the sub-region is, you know, even the algorithm will probably work easier, faster, and nicer if you really just focus on whatever you really want to do. So that's good to keep in mind. I have another thing I wanted to talk about. Is just some nice feature of Avizo which didn't fit in anywhere else. So I'm gonna show this here now. and share the screen. And,
I want to demonstrate another useful feature of Avizo, which Avizo calls connections, which are especially useful with multiple views, and you've already seen them before. So in order to demonstrate that, I'll create a small example. I've loaded our data here. Let's attach an author slice to see it. And we have seen in the Watershed algorithm that we have to compute, or the algorithm actually computes a gradient image which is necessary for the algorithm. And you might want to compare the gradient image, for example, to the original image to get a better understanding of how the algorithm works. So to do that, we compute the gradient volume actually here now of our data set. We can do that by going to image processing, edge detection, gradient, and image gradient. Let's create that. We have a few options. I just changed the interpretation to 3D. I don't want to compute it only in X, Y, because I assume that the Watershed also computes it in 3D, and then leave the others as the default values. So hit apply. This takes a few seconds, but it's already done. And we have our gradient image. So we want to compare it. So one interesting way, an easy and fun way to do that is that you have this, the connections between the modules is this little line here. And you actually can grab it and just connect it to a different module. So if you're now connected to here, you see the edge detection. But with the parameters, of course, of the original data, so you might want to change them to get a better view. So I'll do that back, connect it back to its original module, and just create another author slice here. Now we see the gradient image here with better parameters because they have been now calculated for this data set. And we want to compare it to the original image, so I can turn it off and on. That's also already quite useful because it's just overlaying and showing both. And if I turn this off, I see only the other. But I want to do it actually in a split view. So I split this view, and I see my two data sets next to each other. But this one I actually only want to display on the right side now, and the other way around. This one only on the left, and this one only on the right. Okay, so we see these two images next to each other, and I can zoom in both. And if I zoom in here, I also have to zoom in on the other view, approximately the same view. That's a bit tedious and not easy to do. So there's a nice feature in Avizo which is called linking the views, and you just do this by right-clicking in one of the two, doesn't matter which one, and you go to link camera to, and just click into somewhere in the other view. And now actually these two cameras are linked, and if I now zoom in one, the other one zooms is actually the same, and the other way around. If I do it here, also both of them zoom nicely. So that's already quite useful. Of course, that doesn't only work for zooming, but also for panning. If I now want to pan to a different direction, both of them pan the same way. But the problem is, possible problem is if you now want to look at a different slice. Let's say I'm in my original image, I want to not look at slice 253, but let's say go somewhere else. Then the slice changes, and then I have to change the other one to the same slice, 370. So I go there and change it to 370 to compare these two now. And that's also rather tedious, and actually can be done in an easier way, and this is called the connections. And this is done here using this little icon, which is supposed to represent the chain, I guess. It's called a connection editor. And how it's done is you have to select both author slices. And don't connect the author slices. So we select both of them. Just press Shift. If you click the second one, and now we see both of them here. And now if I take this one, and if I click it, I see that I get the connections to each of its optional parameters. And I can now actually take the slice number and drag it to the slice number of the other slice. And now these two have a closed chain here. And you also see that they're linked by this white line between them, the two. And if I now change a slice in one of them, also the slice in the other one changes. So here now you can really nicely browse through two different representations probably of the same data set and compare them. Of course, it also works with the other one. If I change this one, also both of them work. And now you can actually just select one. Still, the link is there. I can compare both of them. Zoom in, still, they're also linked. So they're now completely linked. The cameras are linked and the slice numbers are linked. So I can explore both of them simultaneously.
All right, so that's often rather useful if you have want to look at something in two different ways, but just make sure that they're synced all the time. That's good. So we come already to the last video for this workshop, which is actually a bit of an overview of the Avizo GUI. I'll try to be more show you a few of the options you have and a few things that, in my opinion, are just good to know as a generic use for Avizo. And just start the video and share the screen. There we go.
So I want to talk a little bit about the GUI and the general use of Avizo. This is not going to be a comprehensive overview of all the capabilities of Avizo. First, I think that would be boring, and on the other hand, it's too much, and it's too complex a program so that we can do it in just an hour or so. So I'll give you a few hints, and I think what, in my opinion, are useful features of the GUI. So that you can get started and explore the rest yourself. Let's just open some data. Let's say the skull, doesn't really matter. And let's attach something. So we see something. I still have the Watershed model here, so let's use that. And here you already see something. I have done something before, so my camera is somewhere, and I don't see anything. The first feature, I have used it probably a few times already, is you have these 4 buttons here to actually align your view. The left one is just center your object in the middle, but keep the camera the same. So if I move it again away, if I press this button, it just centers. And these are move them axis aligned in the center of the view. But these 4 buttons are rather useful if you're lost somehow. You moved around a lot, you don't know where your objects are, you can always get back to them by using these buttons. Similar is you have a home button. If you press that one, that's rather useless at the moment. But let's say you found some orientation or move or view of your data that looks interesting, or you might want to return to later, something like this, for example. Then you can press this set home button. And now if you go somewhere else, move somewhere, you don't know where you are, with the home button, you get back to that same position. So that can be useful as well. Let's also attach an author slice. So here you see that these are the axis aligned views. If I disable the volume rendering, here's the XY direction. YC, you only see the plane. So let's turn the volume rendering on again. And YC, you see the plane from a different direction. Okay, so these are useful. That one button here, which says seek, lets you actually select. Let's say you have a lot of objects, many more, and your slice is just a small one somewhere, let's say on the top right. You use the seek button and press it, select it, then Avizo will move it somehow in the center. It's sometimes useful. In this case, probably not zoomed in enough, so you might have to adjust a little bit, but it's rather useful. Okay, so you already know these 4 buttons here. This is the zoom, pan, and rotation. You also have this one here, rotation, which just rotates a little bit clockwise direction. I'm not quite sure about the usefulness of this feature, but it's there. And this one is you can change actually interactively the slice. You know that you can now slice through your data. Okay, so these are the basic interaction buttons here, rather useful. Let's go a little bit quickly through the rest of the buttons there. Those that are useful here, you can change between perspective and orthographic projection. Not really that important. Here you could set up a stereo if you have some kind of stereo device. If not, you can ignore it. The next one is this one is actually useful for example, selecting ISO values for an ISO line. You can pick it. You have to, however, have the arrow selected. So, for example, here, if you look at the status bar, it just says ready. If I do, nothing changes. If I use the arrow, you actually see the information of the values, the pixel coordinates, and actually the value of your gray value. So you see here we have gray value 78, and so on. So you could, for example, try to find, if you think there would be an interesting isosurface here, it should be somewhere between, somewhere around 50, 53 or something like that. So that can be useful for inspecting your data. Another thing is that you can actually make measurements. That's sometimes useful. If you just press it, you want to know what's your distance from here to here. You press it and you see your distance in the units that you have selected when you loaded the data. That's important. But you can then move them later on, measure something different. And you can actually expand that and type in some notes or annotation, whatever you want. So you can actually also use this, annotate an image for a paper or a poster or something. It can be quite useful. If you want to get rid of it, just take the module that has been created and delete. And the third one here of these buttons is actually the probe. I did that continuous update and I was confused. I confused it with this button. This is a different one. This is actually pick. So if you pick that one, then you can select an object in the view, and the Avizo will bring it up in the properties panel. It can be useful if you have a lot of objects or you're exploring some project that you did not create yourself and don't know exactly. Then you can quickly select the objects in the view. The problem is that it doesn't work with everything. The water, for example, if you wanted to. So if you have the author slice selected and now you want to go to the volume renderer, you try to pick it, nothing changes. So it only works essentially with geometric objects, but then it can be useful. Okay, the next one will be the screenshot. Let's talk about the other ones first. Here you can split the view. We've used it and I have talked about it, so that's rather useful. You can split it vertically, horizontally, and into 4 views. Here you will have a full screen option if you wanted the Avizo to be in full screen. I usually don't like that, but you can do it here. And that's if you want to just disable things in all 4 views now, press this one, then you can do it at once. You don't have to click things 4 times. What I wanted to show is this views has some little consequence with the screenshot. The screenshot is of course a simple matter. You press the screenshot button and you can now make a screenshot of your view. Here you have an option, capture all viewers. You can select that or not. So if you deselect it, you will only make a screenshot of the one view that you have selected and select this one, then you will get a screenshot of all 4. So we're not seeing anything on all 4. Let's, why am I not seeing anything? Because I'm somewhere else. It's interesting. Something like that, for example, and then you make a screenshot, you say capture all viewers, you will get a screenshot of all these all these 4 views. And if I deselect it, I will get one now only of the lower right, because this one is the one selected, which you see with the white border. Also interesting is probably that you can do an off-screen rendering of the view, which means essentially you can choose your resolution yourself, which can be helpful if you need a high resolution image of your results for a poster, for example. You can choose exactly the resolution you need, and Avizo will save the picture in exactly that resolution, whichever size you want. And you have the choice between a few different image formats. So that's nothing very surprising here, but good to use, and of course that's something you probably use all the time. Let's now quickly go through the rest of the GUI. The menu is, of course, just a basic or a regular menu that you have with all kinds of GUI programs, so I won't spend much time on this. I just want to mention again that the Save Project option is dangerous in Avizo because it simply overrides the existing project, so you probably better want to use all the time just the Save Project as. You can have some edit properties. Here is something interesting. You can change the view of your project view to a tree view. That looks much more complicated. Can be useful if your project is complicated, and you can group things and just make them invisible, show them again. But for smaller projects, regular projects, the better view is probably this tree view. You have the same button here. You can just switch back to the tree view, and you have this thing. That button here actually is probably if you have a larger project and your stuff is extremely not very tidy, so just lying around and getting difficult to see where things are. This has a simple algorithm to lay out your other modules automatically. Okay, but that's that. Nothing more very interesting here. The windows is probably useful to know in case you sometimes you might close one of the windows accidentally, like say the project view, or you didn't need it and needed more space and you have closed the window. You can always bring it back in window here, down, project view comes back. That's also good to know. Anyway, the one thing I wanted to really mention here that you really should use a lot is actually the help in Avizo. It's a commercial product, and that's what you see it in the help. The help is here, really useful. If you use to other programs where if you have a problem, Google the answers. That's usually not good with Avizo. It's much better to just use the help. So you have a user's guide here and some examples. These are the 2 things I'm going to talk about quickly. I just again want to show you that you can simply just bring up this help for each module that you have created. So if you need to know more about this module, you just press the help button, and it's really useful, really nice. You have a description, you have all the features on this panel with pictures nicely explained, and if you use one of those modules a lot, you probably want to at least once go through the help to see what features it has and how it works. Another nice thing is, for example, if there's a more advanced algorithm, like for example the Watershed algorithm that we've been using, if you go to this help, again you get a description of all the ports and things, but also you have often more information, like here, see the fast watershed principle. So just click it and you actually get a description of the algorithm, how it works. And not only that, actually since Avizo started from a research project, they actually often give you the actual references to research papers which the algorithms are based on. So if you want to have really a lot of more information on the algorithm itself, you could even now Google that paper and try to read it. Okay, some words about the user's guide. Of course, explore it yourself. That's what it's there for. You have nice tutorials, nice documents about getting started, things we have done today. But now in the written, you can go through this at your own pace. So this is the start page. You can always get back to this one by pressing this home button here. We also have a link to the Learning Center on YouTube. There are a lot of videos there. I have put the link also on the web page, but you can go here directly. It will open a web page, and you get this Learning Center by Thermo Fisher, which has a lot of videos, I think 42 at the moment, on how to use Avizo for all kinds of things. Some videos longer, 20 minutes, some rather short, just a minute or so. So you can browse through these and see if you find something that's useful for you. You can also look at these official videos. Again, the link is also on the web page. And then, so if you're new to Avizo, it's probably a good idea to go through this help a little bit and get used to it. And then actually also do the tutorials. There you have actually specific problems worked through, like image segmentation. You go to that one, you get a nice description plus a step-by-step explanation how to do these tutorial actually. So if you just want to go through the steps of the tutorial, you just look for the bullet lists. Each bullet list is a step that you have to do, and then you have some explanations, and each of the bullets again is a step. And if you go through it, you should get similar results like this segmentation here. So these are really very nicely worked out tutorials on all kinds of problems that you see here, like segmentation, just reading images, visualizing 3D images, vector fields. If you want to create animations, you probably want to go through this tutorial at least once. You have large data and things like that. But also a very nice thing in Avizo here actually are the examples, and I want to show that because it's not completely obvious. You have a lot of examples. Which ones are available depends on the license. In this case here at Chaos, the license we have, and we have most of them, but not all of them. And show that in a minute. Let's first go through the basic ones. We definitely have those. So let's say you want to look at this example, whatever it is, distribution of pore diameter. Obviously, a sample similar that V1 had, and you get this segmentation. The nice thing here is you have the links, and if you click on the link, Avizo actually loads this project now in as a project. I still have the screen split, I remove that. And that means that you can, let me move it down a little, you can actually just interact with it and play around now with that example. It's just a regular Avizo project, so whatever you do, you can turn on and off things, turn off the bounding box, change the color of the bounding box, play around with the settings of the volume rendering, try to figure out why they use these settings they have here, and so on. If you go to the next example, here are the results of the segmentation. Of course, I've changed things, so Avizo will ask me to, if he has to save it. Here you actually have a split view, or not, whatever you prefer. And here you have the segmentation of these pores now. So you can go through all of these examples and just click on the links, and you will get exactly that result. Let's, for example, this electrostatic fields. You click there, you get the electrostatic field. The Avizo always goes back to whatever reason to my split view. Doesn't matter. Okay. So I said that it has a lot of different examples here with different extensions. So actually, it depends on what license we have, and you can figure it out by just trying it. If you try this one works obviously. Not gonna try the other ones. Just the last one to show this one does not work. So we don't have a license for that. You get errors that when you load it because the modules cannot be loaded because we don't have the license for them. But anyway, that means you have a lot of examples here that you can go through. Look if something is of interest to whatever you're doing, then you can just load the project in Avizo and play around and try to figure out how it works. And in this way, try to learn Avizo and all its features and use it for your research.
All right, so this was the last video. We are at the end of this workshop. Thank you for watching. You should receive an email when it's on YouTube. You can watch it again and let me know what you think. And otherwise, stay safe.